Hi guys, and welcome to today's video on the exact distribution of the sample proportion. Tell you what, these titles get longer and longer and longer, don't they? But the good thing is this is video number 2 of 4 dealing with sample statistics, following the Cambridge Essentials textbook, which I'm using to deliver to my students. So if you're watching, thanks very much for watching. If you're out there in internet land, hey, it's easy and wonderful to have you along. Now, as I normally do, I'm going to recap what we learned in the last lesson. And I suppose the most important stuff that came through was the difference between P and P hat. So P is our population proportion and P hat is my sample proportion. Now my sample proportion is effectively the number of people I'm taking out of my population that have a success or a characteristic I'm looking for. And I think one of the ones I was looking for recently was if I had a group size of 17 people and I chose 6 people from that, I'd want to maybe see how many of those 6 were girls. And what's really important to note is that the number of girls in that group will change. For every 6 people I choose, I will probably end up with a different number of girls. I may end up with a higher probability of 3 girls being chosen than 1, but that's very much what this video is dealing with. And at the end of the last lesson we said that P hat basically is a random variable, and as such, if it's a random variable, it means we can use all the statistics we've done in the videos before. You're going to go, what videos? And I'm going to go, really? They're all on my YouTube channel. Dive in and have a look. So, making sure we understand the difference between population proportion and sample proportion, I want to go and just highlight where people tend to find this confusing. All of the work we've dealt with before, and let's say an example here of find the probability of obtaining exactly 4 heads when a fair coin is tossed 7 times, or a fair die is rolled 50 times, find the probability of observing exactly 10 sixes, blah, 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 blah. What we notice with all of those questions is that my sample size and my population size are exactly the same. And as such, we could use the binomial formula to find those probabilities. Sadly now, our sample size and our population size are actually going to be different. Now I'm going to use an example which is directly lifted from the Cambridge Essentials textbooks. Why? Because it's a fabulous example, and thanks to Cambridge for letting me use this to support my teaching and put on this video here. It actually highlights all of the areas of mathematics that we're going to use for the rest of this chapter. And if you get this question, I'm pretty sure you'll be able to get pretty much all the rest of it we're going to deal with. So we've got a bag containing 6 blue and 4 red balls. So I'm going to write blue is 6 and red is 4. Now you're going to say, why have I written that? All in good time, grasshopper, it's coming. From the bag, we're going to take a sample size of 4. So what that means is that I'm going to put my hand in and I'm going to remove 4 balls. We are now only going to be interested in the proportion of the balls which are blue. Now, we know the population proportion is 6/10. Why? Well, our population describes the whole thing. Our whole thing had 10 balls in it. And how many were blue? There were 6. So our value of P is 6/10. Is that going to be important to us? Maybe, maybe not. But it's important to know that that's my population proportion. My sample proportion is going to change. Why? Well, every time I take 4 balls out, the number of blue balls that are possible to be there can vary between 0, i.e. there's no balls, 1, 2, 3, or 4. There can't be any more than 4 blue balls if I'm only taking 4 out. And so what you'll notice is my value of P hat in the table is given as a fraction. Why? Well, because P hat is sample proportion. And so what we're saying is 0 out of 4 balls were blue. 1 out of 4 balls were blue. 2 out of 4, 3 out of 4, and 4 out of 4. So that now explains where these 2 rows of my tables come from. It is important to note that when I'm taking a ball out of the bag, it stays out of the bag. I don't take it out, have a look, and put it back in. That's not choosing 4 out of the bag. So now I need to find the probabilities at the bottom of the table, and there's lots of ways of doing it. We'll come back to the combination theory in a moment, but what I'm going to say is, well, for example, if I want to find the probability of there being, let's say, x is equal to 0, where x is my random variable saying the number of balls or blue balls. If I want to find the probability of x equals 0, what I'm saying is no blue. So I'm taking 4 out, which would be red, 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 and red. So red first time is, what do we say how many red balls there were? So there were 4 red. So that would be 4 out of 10 times 3 over 9 times 2 over 8 times 1 over 7. Remember, these balls are being taken out without replacement. So in that case, all of those 4 are going to be red. So when I fire up my calculator, I'm actually going to do 4 times 3 times 2 times 1, which is my top value of 24. So that was 24 over 10 times 9 times 8 times 7, which gives me 5040. 5040, which when I simplify that on my calculator, I just so happen to get shift equals 24, copy and paste that one to there. Although I didn't want to copy, so copy there and copy this and press enter. Gives me yuck. That's because I'm in a decimal value. Let's go back to 1 over 210. So I now know that that value there is 1 over 210. I could write that in my table as 1 over 210. Thank you very much. So that would mean trying to find x equals 1. So with 4 spaces, and one of those I could have, what would that be? Blue, red, 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 and red, blue, red, red, and red, red, blue, red, or red, 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 blue. And then I could go on and work out the individual probabilities of that. So blue would be 6 over 10. Times red would be 4 over 9, 3 over 8, and 2 over 7. And I would keep having to do that all the way down here and add the fractions together. But it just so happens we can use combination theory to help us with this. Now, this works very well with small samples or small populations. So first things first, what I'm going to do is I'm going to try and say to myself, well, look, I'm choosing 4 balls out of 10. How do I do this using combinations? Well, as it so happens, I can say 10C4. I've got 10 things to choose from, and I want to find the total number of ways of choosing 4 from 10. Loading up my calculator and going into my catalog and N, and there's my NCR. So I just go, what was it, 10, comma 4, close that bracket, and out comes 210. So there are 210 ways in total of me choosing that. Now that looks vaguely familiar. Well, there you go, ladies and gentlemen. There was my 210. Now we're going to look at the probability of getting no blue balls in my sample, which means that I have to get 4 red balls. Now, the reason I write that now is because I'm going to say, well, how many blue balls do I have to choose? There are 6 to choose from, and I want none, which means for the 4 red, I need to have all 4. See what I'm doing here? It's combinations. Now 6C0 I know from my calculator is 1, and 4C4 is 1. And actually when I multiply those two together, because I'm looking for no blue and 4 red, and is multiply, gives me a grand total of 1. So to have blue 0 and red 4 is one way out of 210. OMG, there we go for that 210. So how do I now get 1? Well, I want blue 1, and that will give me red 3. So 6C1, because I want 6. I've got 6 to choose from and I want 1, and I've got 4 to choose from and I want 3. Now 6C1 I happen to know is 6, and 4 choose 3 I also happen to know is 4, and multiply those two together gives me 24 over 210. And I can continue doing this until, ladies and gentlemen, out comes my sampling distribution table. Wow, this is seamless. There you go. You notice my 1 over 210. There was my 24 over 210. And as I continue through, out come my various probabilities. Now, just to explain what this means. This means there is a 90 out of 210 chance of getting 2 blue balls out of 4 for my population that I have. Now, there's my p-hat. There's my sample proportion. Really important to know where these fractions come from. And there is my probability of p-hat equals p-hat. Again, the probability of getting this value here. That's all that p-hat equals is it's the probability of getting a sample proportion of 0. Now, sampling from a large proportion, When we start looking at very, very large samples, we can't use that system there. I mean, we could, but we'd be there forever, and I think my calculator would break. So when the sample is large, we assume that the probability of observing the attribute we are interested in remains constant with each selection. That's interesting. So, like we did with the normal approximation to the binomial distribution, we can use exactly the same idea. So, large populations, we can use the binomial distribution. So long as there is an idea of only two choices, remember? Going to school and not going to school. Owning a car, not owning a car. For large values, we're going to use binomial. Right, suppose that 70% of all 17-year-olds in Australia attend school. I don't know why the other 30% aren't. We now know then that P, our population proportion, is 0.7. Assuming we're looking at the number of 17-year-olds who attend school. It's binomial because they're either going to attend or they're not going to attend. So if we select a random sample of size 4 from the population of all 17-year-olds, we don't know how many 17-year-olds there are, but we can use the information to help us find my population, my sample proportion p hat. Right, so the good thing is we're dealing with a sample size of 4. So I can draw my first row easy, number at school in the sample. We're either going to have no people at school, 1 people at school, 2 people at school, 3 people at school, or 4 people at school. To go from this top column to my p hat is really easy. It is the value here divided by my sample size. So that would be 0 on 4, 1 on 4, 2 on 4, 3 on 4, and 4 on 4, which is where they get their decimal values from. So now the question is, where do we get these probabilities from? Where does this 0.0081 come from? So loading up my calculator and using binomial, we're going to interactive, distribution, discrete, and binomial PDF, not CDF. We don't want a range of values. We just want the one value. Now it says X. What's your value of X? I want 0. Number of trials is 4 because that's what I'm taking out. The probability of success is 0.7. Hit enter twice and out comes out really, really revolting 8.1 e minus 3. But the good news is that's just standard index form for this value here. If I just want to check that one more time to see what happens when I put 1 in. Now, don't think, for example, that you are going to put in 0.25. That's not what they're asking for. They're actually asking for that top value of 1. And when I hit enter, out comes 0.0756. Put 2 in, and yes, out comes 0.2646. So we can use our binomial distribution to go from these values at the top. So long as I know what my probability, my population proportion is, I can get these values on the bottom. And you're going to say, well, what's the point of this middle column? All in good time, grasshopper. So I've explained what that means. But using this table and the information we've had with the binomial, we can find things like the mean and the standard deviation. I'm just going to make it a bit smaller so that my head doesn't sort of squidge things out of the way. If you remember, finding our mean from a probability distribution table was freaking awesome. If I wanted to find the mean for this table, and I want to call that the mean of p hat, then I'm going to do this times this plus this times this plus this times this plus this times this plus this times this. Why? Because we knew that previously the mean, or the expectation of x, which in this case is the expectation of p hat, is going to be equal to the sum to p of p hat times the probability of p hat equals p hat. Yeah? Whoa! That is freaking awesome. Sorry, that shouldn't be a P there. Let's put that as X to stand for my values of 0, 1, 2, 3, and 4. So that is my mean. We can work out our variance in exactly the same way. Now, I know it feels like I'm rushing this a little bit, but actually a lot of this theory is just given to you. There are ways to prove it all, but again, sadly, it's a little bit beyond this video and possibly beyond the course. So, our variance. If you remember, when we had the variance of x before, we had the e of x squared minus the e of x all squared. Well, the same thing works for p hat. We're going to find the e of p hat squared minus the e of p hat all squared. How do we do that? Well, we're going to get, by all means, please go back and watch the previous video. But in the same way as we already have this value here when we work out the mean, we can use the same theory to find out that the E of p hat squared would be equal to the sum of x of p hat squared times the probability of p hat equals p hat. Okay, so there's the formula for the mean. There's the formula for the variance. And we know, as is standard, that our standard deviation is given by the square root of the variance. Now, interestingly, if I was to do those multiplied together, added to 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 those multiplied together, guess what value I would come out with? Well, actually 0.7. And you're going to say 0.7, that sounds familiar. Well, it happens to be, yeah, my population proportion. So I now know that the mean, or the expected value of my sample proportion happens to be my population proportion. That's going to come in really, really useful in about 3 or 4 minutes. So we can also use theory that, again, is slightly beyond this video to say that the standard deviation is given by that formula there. So really, really important that when we're dealing with sample proportion for large values of n, the mean is given by p, and my standard deviation is given by the square root of p, 1 minus p over n. You're going to be using that ever such a lot shortly if you're following this course, and in fact any course that you're doing. So the question is, how do we use this theory in the questions? Well, here is an example from the Cambridge Essentials textbook. And again, a freaking awesome example. Suppose that 70% of 17-year-olds in Australia attend school. Okay, so same example. So I now know that my p is 0.7. Do I have a large data set? Well, yes, it's dealing with all 17-year-olds in Australia. So I can now automatically write that mu is also equal to 0.7. If a random sample size of 20 is chosen, so n is equal to 20, from this population find the probability that the sample proportion, so the probability that p hat is equal to the population proportion of 0.7. Now, going back to my table before, this column here is really, really important. If we knew the x value, do you remember we could then find my p hat value? Yes? If we knew the x value, we could find the p hat value on the condition that we also knew our sample size. Knowing this x value then allowed us, using our binomial PDF, to find each of the values below. So, have they given me all the information that I need in this question? Well, what I've done is I've just sort of sketched part of my table, because I'm a very visual learner and I like this idea. So it's telling me I've got to find the probability. So I know the probability is the very bottom row when my p hat equals 0.7. So I filled in my p hat of 0.7. I know that it's got to have some sort of value of x on the top. And when I know that value of x, I can find my answer. Right. But how did I find my value of p hat? Well, I know that p hat is equal to x divided by n, where n is my number of trials. So I know that 0.7 must be equal to the x value on the top divided by 20, which is very much what that line there is saying. Rearrange things around so that I get x is equal to 0.7 times 20, and out comes my value of 14. Now, why is that important to me? Because once I know this value here, I can use my calculator to help me find that value there. So, loading up my calculator, interactive, distribution, continuous, binomial PDF, x value. I know my x value, thank you much, is 14. I know the number of trials is 20. And I know my pos is given by 0.7 because 70% of Australians go to school. Hit enter, and out comes 0.1916. Booyaka! So impressed. And yes, ladies and gentlemen, there is my 0.1916. Now you're going to say, hold on a moment, that slide seems to suggest that you used the other formula. Absolutely, it still works, but my calculator just makes it a bit quicker to do that. So there we go. There's the probability. The probability that my sample proportion is equal to the population proportion is 0.1916 to 4 decimal places. Part B. The probability that the sample proportion lies within one standard deviation of the population proportion. Ooh, the sample proportion lies within one standard deviation. So the minute I see the word standard deviation, I know that I've got to find my value of sigma. How did I find my value of sigma? Well, earlier we said that sigma was equal to the square root of p, 1 minus p over n, just using that formula. And I knew that p was equal to 0.7. So here is my formula restated, and then substituting in my values gives me a sigma of 0.1025. Right, and I want it to be one standard deviation either side of my p hat. I want it to be one standard deviation either side of that. Right. So we are looking for mu minus sigma is less than or equal to p, which is p hat, which is less than or equal to mu plus sigma. So we know what our value of mu was. It was 0.7. Large sample, mu is p. So there's my 0.7, and I'm going to take away one standard deviation, and I'm going to add one standard deviation, which just so happens to give me the probability of 0.5975 and 0.8025. Now, let's just go back and remember that what that has now given me. Here is my table. Here is my x. Here is my p hat. And here is my probability. Now, we are looking for the probabilities between the two values of 0.5975 and 0.8025. So we've got this middle column. How do I go back up to the top column? Well, I multiply it by my sample size, which was 20. So there we go. There is my equation. And that tells me that my x value for that would be 11.95, and my x value for this would be 16.05. Just using that formula there. But we have an issue. Because although that makes sense and we've done the basic calculation, because we are dealing with the number of students, we cannot have 11.95 students. We can't have 16.05 students. There's pretty much not a student walking around with just 0.05 of themselves. What would that be? A hand, an arm, slopping along the floor? Probably not. So because we're dealing with whole numbers and because it's binomial, and big hint here, ladies and gentlemen, binomial is tricky if you don't remember. We round 11.95 to 12 and 16.05 to 16. So what we want to do is come slightly in between the two outer values that they give you. So slightly bigger than 11.95 and slightly smaller, or the nearest whole number, inside of 16.05. And knowing that, we can now fire up a calculator. Now in this situation, loading up my calculator, I do interactive, distributions, discrete. I now want to use binomial CDF. Why? Because we're looking for a range of probabilities between two values. My lower value, as I say here, is going to be 12. My upper value is going to be 16, taken exactly from the question. My number of trials was 20, and my probability of success was 0.7. Hit enter, and out comes 0.7795. Ladies and gentlemen, there is 0.7795. Now, the last part of the question states, part C, that it wants two standard deviations either side of the population proportion. And again, so in this situation, I'd want to do mu minus 2 sigma between p hat and mu plus 2 sigma. Now in this situation, I'm not going to do that. This video has probably been long enough. I'm just going to cut this one short here now and leave that as an exercise to you. But the ideas held in this are critically important, particularly the idea about going from p hat to an x to an actual probability using the binomial is really powerful. I'm going to leave you now to actually have a bit of a play with that. This video has been on the exact distribution of the sample proportion. I really hope you found it useful. There will be more videos coming, and hopefully you're enjoying them. There's lots and lots of them on my YouTube channel and my website. Now, have you subscribed yet? No? I'd be deeply grateful if you could. And actually, why don't you put something out there on, I don't know, VCE discussion space or Facebook or Instagram, and just let everyone know there's a resource here for them to use that hopefully is well explained. Subscribe. Otherwise, do me a favor and load the next video, which is loading over there as well. It's been really good seeing you. Thanks for taking your time to get to the end of this video. I look forward to seeing you on the next one. Take care.